the very last talk of this Thursday, and it's a pleasure to have Sayan with us, and he'll tell us about how many directions determine the shape.
So first of all, I'd like to thank the organizers for even inviting a Bayesian statistician here. So, and I'm going to give a talk which is going to have a lot of pictures because it's the last talk. There'll be a few equations, but we'll try to keep that to a minimum. And I'd like to thank my collaborators on the theory part, Justin Curry, who's at University of Albany, and Kate Turner, who's at the Australian National University, and my colleague at Duke, Doug Boyer, who's a morphologist. And then on the more applied end, which will be at the end, Lauren Crawford is at Brown, and Anthea Manod, Raul Rabadán, and Andrew Chen are all at Columbia. Okay? So I'm going to start with a picture. And so this is from Stephen Jay Gould, and the point I'm trying to make here is that one of the geniuses of Darwin, and I think thought that led towards evolution, is pre-Darwin, the systematists and people who were studying organisms and classifying them fell under the Linnaean system of classification. And there what you had were these Platonic ideals of objects. You had the ideal wolf, you had the ideal dog, you had these ideal blah, 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 blah. And the point I'm trying to make here is that Darwin started saying, well, the interesting thing is not the ideal, it's variation. So what I'm really interested in is variation in shape. And in this case, it was variation in the shape of a beak. For my colleague Doug, he's interested in the variation in bones. These are specifically heel bones, and these are of various extinct and extant primates, okay? So we might want to understand variation in this. And one of the reasons we might want to do this, if I can tell you how similar these bones are, I can build a similarity matrix, and from that, I can build a tree. Now I can ask the question, how does this tree made from these traits or phenotypes differ from a phylogenetic tree? And this might start suggesting the question, was there selective pressure on the shape or this trait? So this is a question we will come back to, but we'd like to get to. Now, there's this picture that I want you to have in your head, and we'll come back to this, and this is of thinking about evolutionary trees as broccoli. So if I live out here along the leaves in these florets, this shape is probably really similar to this shape. And maybe even a diffeomorphism or a continuous transformation will work. But if I come all the way down here to an old ancestral organism and then come back, diffeomorphisms or something smooth may no longer be meaningful in terms of a change in a shape, right? So that's a picture I want you to have in your head. Okay, so that's why broccoli is here.
Sorry, but in this case, if you go back, it would be similar shape, right?
If I come back here.
Then if you go back, I mean, for broccoli, my broccoli.
Yes, thank you, yes.
Okay.
This is a property of broccoli. But I'm decorating the florets of broccoli with shapes. I'll be doing a lot of decorating things throughout the talk. So classically, there are three models of shapes. The first is Kendall's shape space, and I'll touch on that. The second is this idea of diffeomorphisms, and it goes back to the kind of this Grenander school of continuous transformations and a variational problem. And the third approach, which will be very much like what I'm going to talk about, really comes from the people who studied random fields. And so this is Keith Worsley did a lot of this work when he was studying MRI, and it's looking at excursion sets. So I'm going to come back to thinking about excursion sets and integral geometry. Okay, we'll get back to that. Okay, so back in the day, the way Kendall thought about shapes is you put down a bunch of landmarks, okay? And then once you have these landmarks, you put a vector at each landmark, and you just stack them together, and this gives you a matrix. And a similarity between two shapes are distances between these two matrices, modulo rotations, translations, and scalings. So this is formally what shape space is. These are the landmarks. And the Procrustes distance between two shapes is just the squared distance modulo these rotations. And this actually forms a space which is technically not a manifold because it has cusps in dimension 3 and above. But this was shape space. Now, what is now interesting and true is that it's not like the old days where your data is you'd go to the British Museum, you'd take an object, artifact, put down 5 points, and say, hey, these are other 5 points, and how similar are the 5 points? Right? Yeah?
Can you go back to the definition? So in the equation, you allow a single rotation, translation, and scaling?
Yep.
It's quite limiting, right? I mean, if I have...
Well, take it up with Kendall.
No, I'm asking.
Well, what he was saying is that for any two objects, right, his idea was two shapes. Okay, so the way that he thought, and I think it's actually reasonable to think, is that you have biological variation and you have technical variation. And what he called technical variation were things that were the same modulo scale, rotation, and translation. Right? Otherwise, he said they're different. Now, it could be for one object and another object, you could have different ones between pairs. Right? So this is typically done pairwise. I will touch on later on what happens if you have a bunch of shapes and you want to do it across all of them. That's a much harder problem. Okay? Okay, so what we have now are really nice databases where we actually have a bunch of CT scans. So we have much richer data than these 5 points on, from the British Museum. And I wanted to show you two pictures. These are what you can download, right? This is some like toad-like organism, right? And you can actually go download the CT scan. And if you actually look at the data itself, this is what it looks like. The data itself, this is called an off file. You get a bunch of 3 coordinates in 3 dimensions, and then you get, okay, 0.8, 0.7, and 0.0 get mapped together in a face, right? So you get these coordinates and how they mesh together in a face. And the point I'm trying to make here are these data come as simplicial complexes. And if you don't know what that is, I'll define it in a second, but that's the intuition I want you to get. Now, another approach, and this is something that my colleague Doug Boyer and Ingrid Debashis have been working on, and I've been working with them, is the Divyamorphism Paste approach. So I take my shape, I put down a bunch of landmarks, I put a little ball around that landmark, and then I define a variational distance between these two, right? And this is one way of thinking about it. Now, I'll come back to this in a second, but I'm going to use topology in a little bit, and I just always like adding this picture, which is why would anyone use topology to model shapes? Because a coffee cup is the same as a donut, right? This seems silly. But the point I'm trying to make is that homeomorphisms are stronger or weaker than diffeomorphisms. And the point I'm making is a lot of these data, so these are fly wings. David Hull's a statistical geneticist. And these are normal flies, and these are mutants. And what you see, they're qualitative differences. You add lobes, you lose leaves, right? So it's very hard to actually do a diffeomorphisms between these because they're qualitatively different pictures among some of these, okay? For example, here we've lost this lobe. So what we're interested in is can we model shapes without requiring landmarks or diffeomorphisms? And our approach is going to be to transform the data into a representation that I can use standard statistical models for. Ideally, this transformation should be injective, so you shouldn't lose information. This transformed space should be nice. In some cases, it'll be a matrix. And I should be able to pull back from the transformed space. So whatever I infer in this transformed space, I should be able to pull back and say something about the original object. So these are my goals, okay? Great. I'm going to use 2 topological summaries to use this, Euler characteristic and persistent homology. I'll demonstrate them by picture. I also might define them. But let me first build up what is a shape, or what I think of as a shape. So these are simplices. So a point is a 0 simplex, line is a 1 simplex, this is a 2 simplex, tetrahedron 3 simplex. Simplicial complex is just a collection of simplices, where all the faces are in the simplex, and simplices intersect along common faces. So I'll give you examples of what's not a simplicial complex. You can't just take this and stick it in the middle. That's not allowed. I can't delete a node, and I can't delete an edge. So these are examples of simplicial complexes. So my less abstract definition of a shape is going to be a simplicial complex. And I showed you that's my mesh, that's my data. Now, when we worked on this, we also thought of a much more abstract version because I was working with topologists who liked category theory. But this will be one of the more technical slides. It's not so horribly important. But what this is telling you is this is a definition of basically measurability for sets. So what you're doing is you start out in 1D and you say you're just looking at finite unions of open intervals. Okay? Then you go to 2D, so you have a product space, and you're just saying when I project back into any of the 1 dimensions, I still have this kind of definition of a shape. Okay? So this is a basic construction which is not so important. Now, what I'm going to tell you is they're constructible sets. These are collections of compact definable subsets of RD that are tame, have nice properties. This is an important idea, constructible functions. These are integer valued functions such that every level set is tame. What do I mean by that? Is if I just sweep through a function, the number of critical points or the smoothness of this is somehow constrained. And I'll make that more rigorous in a little bit, okay? Now, one of the objects we're going to use a lot is something called a height function. So this is my bone, this is a plane, and I'm going to think about sweeping this plane through the bone. And I'm going to do it from many directions. Okay? So this is specifically a CT scan of a mouse heart embryo, and I've swept distance A, and I'm looking at the sublevel set of that. And what I'm going to compute from that sublevel set is something called the Euler characteristic. So in the case of a mesh in 3 dimensions, the Euler characteristic is just the number of vertices minus the number of edges plus the number of faces. So this is a topological invariant. So for all of these filled-in objects, the Euler characteristic is 2. For a donut or a torus, it's 0. And for Swiss cheese, it's negative 34. Okay? That's not so formal. Okay. So if I were to take a hand and I would just sweep from the bottom up, this would be what's called the Euler characteristic curve. So that's as I sweep through, this is telling me how the Euler characteristic is changing. And this is just a smooth version of this. Basically, I subtract off a mean and I integrate. And I'll give you the formula in a little bit. The Euler characteristic curve is changing at critical points. So it's really in a way of counting or collecting the critical points. So that's all I was telling you. Okay, the other summary is something called persistent homology. So homology in general, Betty 0 is the number of connected components, Betty 1 is the number of 1 cycles, Betty 2 is the number of voids, right? So if you take the sphere, hollow it out, it's 1 connected component, there's no 1 cycle, and there's 1 void. What's amazing is these can all be computed using linear algebra, and that's kind of the beauty of the work of Emmy Noether. So I'm going to give you a 3-minute introduction to Morse theory. Okay, so pretend I'm back in North Carolina. Well, maybe I can pretend I'm back in North Carolina, and there's a flood, and the water is rising. And what I'm interested in is when something changes in terms of the connected components of the image down here. So the first thing that happens is you hit this valley. You go a little bit further, you hit another valley. Go a little bit further, you hit this valley. Now the next thing that's going to happen is you get to this peak, and this is going to merge with this. Right? So this has just born. This is a feature that's born. You go a little bit further, it dies. And similarly, you can go through this whole thing, and these births and its deaths, which are basically pairings of critical points, give you a summary. And this is called a persistence diagram. Okay? Another way of thinking about this is after filtration. I take my data, I slowly thicken it, and I start asking, when does topology or homology change? And so if you look at these nestings, you're just asking, when do these homology groups change? Okay, great. Persistence diagram, another way of thinking about it, is a countable multiset of points, and the diagonal has infinite multiplicity. So if I give you 2 curves, the red curve and the blue curve, this would be the corresponding diagrams. And I can define distances between these diagrams using an L2 Wasserstein metric. So I'm just saying, what's the cost for moving the red points to the blue points? And anything I can't match, I just match to the diagonal. Okay? So this is one metric. I'm not saying it's the best metric, but this is a common metric used. Okay, it turns out that from this to Wasserstein, or the infinity version, which is sometimes called a bottleneck distance, there's a stability property. So if the curves are close, right, the ensuing diagrams will be kind of close. This doesn't necessarily go in the other direction, and we'll talk a little bit about that. Okay. Now formally, this Euler characteristic curve is basically, you're thinking about a sphere. I'm taking directions along the sphere, and I'm mapping it to these constructible functions, these things that jump as integers. Okay? Now another way of saying this is take your mesh, go in direction v, okay, go distance t, look at the sublevel set of that, intersect that with the mesh, and compute the Euler characteristic. So that's formally what we call the Euler characteristic transform. Similarly, there's a smoothed Euler characteristic transform. So you take the Euler characteristic, subtract off the mean, and integrate it. Okay? Now what's interesting here is I've turned a mesh into a collection of curves in L2. Now, as a statistician, what's nice about that is I've taken my problem back to functional data analysis. We think about and we have tools for modeling functions in L2. Yeah?
This is integrating over all possible directions.
So this is integrating, well, we'll get to that. Yes, you want to?
What is it integrating over?
This is integrating over the sweep.
Oh, the sweep.
The sweep, okay?
Got it.
Yeah.
Got it.
And you can do the same thing with the persistent homology. You take any direction, you get a diagram, right? You're just kind of doing that 2D picture of that Morse function.
I'm sorry, the sweep is over the radius of your d minus 1 sphere?
Actually, no. You could do it that way. In this case, it's actually sweeping up through the thing. So if I showed you, so it's in the 3D version, it's just sweeping through the object. Okay, so it's really like the Morse function. Okay? Yeah.
So, like in issues, you can keep going, right, and it stays the same. How do you choose where to stop sweeping?
I know how big my shapes are,
Okay.
right? Because like, I get them. Okay. Now just for anyone who cares, there's a commutative diagram between the persistent homology transform and the Euler characteristic transform. And all this says is that the Euler characteristic transform has less information than the persistent homology transform. And now, since we are in a robust statistics workshop, I should say something about robustness. Okay? So, in a way, the persistent homology transform has some Lipschitz property. The Euler characteristic transform does not. But the Euler characteristic transform, when you smooth it, lends to something that's L2. You can work in L2 and work with curves, whereas the space of persistence diagrams is terrible. It doesn't have unique geodesics, and there are a lot of problems with it. And again, part of the reason why we're going to these integral transformation ideas is to be robust with respect to these lack of diffeomorphisms. So I can now define distances between shapes that are not necessarily diffeomorphic. I take the smooth Euler characteristic transform in any direction, just measure the L2 norm of the curves, and integrate it over the entire sphere. Now what this means and doesn't mean we'll come back to, but this is one way of measuring distance. And I could do the same thing with the persistent homology transform. Take a direction, compute the persistent homology of rank k. So k be equals 0 would be connected components, k1 would be number of 1 cycles, measure this distance and integrate it over the sphere. Now there's this question, which is my computer does not want to integrate over the sphere. Turns out, it doesn't like that. Right? So you can ask a question about how many directions, and we'll come back to this. And you can ask a question, is this transform invertible? Right? So this is related to a classic idea which is called the radon transform. So if the way people get micro CT scans in these meshes typically is you take an object and you radiate it from many, 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 many different directions and you reconstruct it. Okay? Now there's a very beautiful result which kind of tells you, this is called Shapiros inversion theorem. And this is probably the most general version of when you can invert the radon transform. And it involves fiber bundles and sheaves, and it's very abstract. So I'll just tell you that this is a theorem. It exists. You can read about it. Now, what we can do is we can use Shapiros inversion theorem to tell you that both of these transforms are injective. You don't lose information if you take all directions. Now, initially, Kate, myself, and Doug proved this without using Shapiros inversion theorem in dimensions 2 and 3 by actually coming up with a pseudo-algorithm that did this. It was like a very much geometric brute force algorithmic-like thing. Then we realized you can just use Shapiros inversion theorem, and so that's what we did in this paper, and around a similar time, Rob Greist and 2 of his students showed something similar, okay? Now, how many directions? We found for dimension 2, you can use 162 directions, and for dimension 3, you need 700 directions. Those are very precise numbers. Now, there's a more serious question, which is, how do I think about this more rationally, right? How do I think about the number of directions I need and think about this problem? And that's what I'm going to spend the next 15 minutes telling you about. Yeah?
Sorry. Any 700 directions, as long as they're different, will reconstruct the...
I was actually joking.
Okay.
Right? I'm just... empirically, when we ran our code and did this on real data, which I'll show you later. In 3 dimensions, we did use 700 directions, and in 2 dimensions, we used 162. This is not yet principled, right? And this goes back to actually the title of this talk. How many directions characterize a shape, or a family of shapes? So we want to think about a sampling theory for shapes. What is some notion of a complexity metric for a set of shapes, okay? Great. There's a beautiful paper by Arnold, and he asks the following question. If I tell you where the critical points are of a function, right? Can you tell me how many homologically different functions exist that satisfy having those critical points? And he gives a closed form solution for this, which is amazing. It's just closed form solution. It's very hard to extend this to 2D because what he does is completely dependent on ordering. And as we know, ordering becomes harder when you go to dimension beyond 1. So how do we think about this problem? Okay, so what we first do is we constrain the shape of the shapes. I'm going to tell you my space of shapes are the set of all embedded simplicial complex K in RD. And they have the following 2 properties. At every vertex, there's a lower bound on curvature. I'll call that delta. And I'm going to tell you in any direction that I sweep it, there's a maximum number of critical points. Okay, so these are the 2 constraints that I need. Okay, given these 2 constraints, this is how many directions you need. So if you want to play 500 million questions, right, and you give me a family of shapes, these are the number of directions that you need to be able to tell apart shapes. Okay, I'm going to talk a little bit about how one gets this and what this has to do with a VC dimension, okay? So first, there's a resolution parameter. You notice there's this 1 plus 2 over delta to the d. And this is the number of points we need to get a delta cover of the sphere. Now, you might say it's weird. Why do you need a lower bound on curvature and not an upward bound on curvature? And it turns out if you think about this for a while, it's really hard to tell apart 2 things that are near flat. Like if you give me a pancake and you give me, I don't know, a street in Amarillo, Texas, right? It's kind of really hard to tell this apart just by sweeping in directions. Whereas if you give me something really curved, a lot of directions will start differentiating things. So that's what's going on here. This is giving you the number of delta covers required to determine all the vertices of the shape using only the Euler curves from the union of these delta nets. That's how we get this. Now, I didn't tell you what Wx is, and so I need to draw an important picture, and I'll come back to that picture later. So here's how you should think about this. Yeah?
Sorry, so is it the case that the bound on curvature, the lower bound, is something that you use to control how quickly the function changes on the sphere?
Yeah.
That's the point?
Yeah. I'm about to draw the sphere. So Dimitri told me to draw a sphere. So I drew a sphere. Okay? And the idea is, what are we doing? We're sweeping in a direction v along the sphere, right? And any direction along the sphere, what am I going to get? I'm going to get one of these Euler curves, right? Okay, which I'm just going to not write like this. I'm going to think about it as a bunch of points, and this is just where the critical points change. That's all that Euler characteristic curve is. It's just telling me where these critical points change. And let's call this direction v1. If I take a small cone around v1 and get another direction v2, and if that cone is small enough, or what small enough means is what Dimitri was saying, which is based on that curvature, then let's call this T1. There's going to be a similar T2, which I'm not going to draw, but there's a linear relation between this T1 and T2. And this is just a result of projective geometry, right? So for a small enough region, so what I'm really doing is I'm taking the sphere and I'm chopping it up with hyperplanes. I'm doing a hyperplane partition of the sphere, is really the structure, right? And all I need to do is know one of these in each partition. Because if I know one, there's a linear function that gives me all of the others. And the number of partitions I need is W of x. And you can basically bound that. And basically, which is by the union of x choose 2. And this gives you a bound on the hyperplanes. And immediately, basically, you get a VC result because you apply the Sauer-Salak lemma to that. Okay? So that's how this cardinality is coming in, okay. Now, one interesting idea that we're working on is actually building likelihood models on these shapes. So if I can basically make a random mixture model, or I pick a random direction V1, model this, right? Get different random partitions, think of this as a mixture model. This is a distribution on shape space, on this moduli space of shapes. I just need to pull it back to the original space, and I'll talk about that later. Okay, now, you might want to do everything in a rotation invariant way, right? Things that I did now are not rotation invariant because the directions had to line up. So this is push forwards of measures, but just think about it this way. Take any direction, think of it as random, I get a curve, right? Now I have a bunch of random curves for shape 1, I have a bunch of random curves for shape 2. You have two choices, fit a distribution, look at some notion of divergence, right? Or look at these as empirical measures and do an optimal transport, right? So this is a theory that says that will go through if there's some generic properties of these objects. And we're actually implementing this and see how empirically well it works. Now, the reason why we went to the smooth Euler characteristic curve is we wanted to build possibly likelihood models, right? So this is an exponential family model. So if I have k curves, one from each direction, what I could do, I have two choices. One, I can discretize them. Each curve, now I have a matrix. Now I've taken a shape and turned it into a matrix variant normal problem, right? So this is a shape now. I model it by a mean of the matrix. Mu is modeling the covariance between the curves. V is modeling the covariances between points in a curve. And this is a likelihood model for shapes, which is not easy to write in the actual space of shapes. If you don't want to discretize, you can model this as a Gaussian process. And I'll come back to ideas related here later. Okay, so these are calcanei from two different angles. And here's real data. I have the heel bones of these 106 primates. Okay, some of them are extinct, some of them are extant. I compute the persistent homology transform. I get pairwise distances. I do multi-dimensional scaling and embed it in 2 dimensions. That's how you get this picture. And these are all great apes. This is a lesser ape. So you start seeing these are kind of folding together. This is not a spider, it's a spider monkey. Okay, this is a baboon macaque. This is an extinct old world monkey. So all of these, except for the spider monkey, are old world monkeys. These are all new world monkeys. This is an extinct new world monkey. This is a squirrel monkey, not a squirrel. And these are all lemurs. So you start seeing something that you expect evolutionarily. And so this is my picture my colleague Doug made, which looks better. And also starts telling you what taxa these belong to. Okay? Now this is I'll make 2 comments. So one of the things that Doug told me is that, at least in one way, this was better, and that the hylobates were now matched with apes, and previously hylobates were with the aluata. So I got this email and I had no idea what it meant. Now it turns out, well, my wife is a biologist, so she explained this to me. She said the gibbons are now with the apes before they were with the howler monkeys. So that made Doug happy. Now you can take a look at this, and this is what the picture is that Doug made when we were using Procrustes, or the classic Kendall method. This is a diffeomorphism based method, and this is our method, so at least visually it looks better. We also did simulations and things like that, which I won't show you because they're really boring.
I'm sorry, what was the original dimension before you embedded it? I was lost.
The original dimension?
Yeah, before you embed in 2 dimensions.
I just have a pairwise distance matrix. There's no dimension. Well, if you
Distance matrix you...
Yeah, so I have it, it's like 7,000, I think. So if you stack, for example, all of those Euler characteristic curves, I think it's like 7,000 dimensions.
So what's the histogram of these pairwise distances?
I don't have that. I have that somewhere in the paper, but I don't have that.
That would be very interesting, right?
Yeah, it would be, yeah. So this was, and we've done other comparisons. There's a very interesting math question here, which is, what is a gold standard? Right? When I ask you questions about diffeomorphic shapes, I have some notion of a gold standard because I have this transformation group. When these things are no longer diffeomorphic, it's not clear what is a gold standard. There is some theory. There's something called the theory of Hadwiger integration and something which is related to Wild's tube formula. And these are things that Jonathan Taylor and Robert Adler have worked on, but those are limited to certain classes. So thinking about generalizing that is actually an interesting question. Okay, it turns out that not everyone cares about heel bones. I think it's shocking, but not everyone cares about heel bones. So we wanted to think about, can we apply these ideas to more biomedical applications? And this is a person's skull and brain, and this is a brain tumor. This is a glioblastoma. And what we wanted to ask is, how much does the shape of a tumor explain clinical variables? Okay? And you can ask, why should it? And we'll come back to that. So I have 92 patients. They have matched gene expression and MRI data. This is my gene expression data. This is a set of morphometric features that oncologists and radiologists decided to use. And they use it in a lot of these TCGA papers where they combine imaging with genomics. These are 5 stupid features, like how big it is, how skewed it is. And this is 7,200. So these are the collection of our topological features. And we have 2 responses, disease-free survival and overall survival. And we're going to do regression. We're going to think of the shapes as covariates in a regression problem. And we're going to ask which of the following best explains variation in the clinical trait. Okay? And we're basically going to use a Gaussian process model. Okay? This is like the Bayesian part of the talk, but I wrote it frequentist because I'm at Berkeley.
So volume should dominate, right?
I'm sorry?
Volume should take over.
Let's find out.
Yeah.
So this is what you get. So this is R squared, which is percent explained. And optimal just means how many times was one of these features optimal when we ran them all, right? And what you find is gene expression is not that great because it's too variable. The morphometric features are decent, but it turns out that this Euler characteristic transform is doing really well in all of these cases. And what you also find is using a heavy-tailed kernel is better, right? So this is kind of interesting in that maybe there's some utility in this and maybe we can get some information out of it. Now there's a basic question which you can ask is, why should topology tell me anything about survival or something else about a tumor? And that's a really good question. Now, there is something that surgeons know. If I have a tumor and it's broken up, so Betty 0 is quite large, the chance of it proliferating and becoming metastatic is larger, right? Something else surgeons know, which is if I have a breast cancer and it's necrotic in the middle, so it's a shell and it's necrotic in the middle, those usually have good outcome. So Betty 2 is a positive thing. So what you're really trying to understand here, and you need experiments to do this, is how does this geometry relate to the molecular biology of proliferation and the physiology of proliferation? That's kind of the underlying question, okay? Now, this is something we're working on right now. You can ask what parts of the shape are most associated to variation in the trait. So basically, can you do variable selection? Okay, so here's an example of a data set we're working with. We have 50 molars from 5 different primate genera. These are the monkeys. Okay, and some of them eat leaves, some of them eat insects, and some of them eat fruits. So this is a classification problem. So what I can do is take the different data from the species, look at the Euler curves, do variable selection on them, so match regions. And the question is, can I pull back and give you a picture like that where in the shape you can, okay? So we're working on this right now. We're debugging things, so I'm not showing you final results, but the basic idea is you can, and it's a problem in projective geometry. So let's say this is my shape. It's just a parabola. It's very simple. And what I'm doing is I'm just looking at, I know the direction I'm going in. I know where there's a critical point, right? So let's say I highlight that. I go to a position really nearby, a cone really nearby. I look at where this is hitting. I look at where this is hitting. And if I take 3 directions or more, I can reconstruct where it is, right? It's just, again, straight projective geometry. So this is the idea that we're using, okay? Now, everything I've told you, in a way, is just signal processing. And it's integrals. These are integrals. They're Euler integrals. They're not our standard, I don't know, Riemann integral. But this is all signal processing. So there's no reason I needed to sweep through the whole shape. I could have done it localized, right? So you can actually think about this entirely as a signal processing problem, and you pick your bases. You can formulate a dictionary learning problem in this, where you pick subshapes or small shapes, and you comprise your shapes. And we're trying to do this actually to simulate interesting shapes. I mentioned this. So this is a problem I really want to work on. So the classic idea in phylogenetics is I get a bunch of sequences, I have a likelihood model, and I have the substitution model, right, between these letters, alphabet letters. Now, in a way, I gave you one likelihood model. Now there's a question of what is a natural substitution model for shapes, right? Doing Ornstein-Uhlenbeck on shapes might be weird because you don't want them to cross each other, right? So thinking about what is a natural substitution model here, I think, is really interesting. So there's a picture that I didn't show you. One way of thinking about what I told you, and also the way of thinking about the diffeomorphic version of shapes, is that this is a shape, 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 this is a shape. It lives on a manifold maybe it doesn't, okay? And there's a graph which kind of tells you which shapes are kind of close to each other. And above each shape I decorated with something. So I could decorate it with the landmarks, I could decorate it with tangent spaces, right? If I decorated with tangents, this would be a tangent bundle. I could generalize this to general fiber bundles. And all I'm saying is that if I go from here to here to here, right? And if I get back, let's say I went here, 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 and then I went back to here, okay? If I get back the identity, right, then I've done parallel transport, and all of these are flat, okay? Which means that they live on a little, nice little floret of broccoli. Okay? Now what happens if you go from here to here, let's say here, and try to come back here, you may not get the identity. This graph may be broken. There might not be a trivial flat section across all of this graph, which is why a diffeomorphism approach may not work. It may work locally and not globally. And so one way of thinking about this is, what happens if I decorated this with these Euler characteristics, right? Does this give me another way of thinking about integration theory, and how are these related, right? So that's also a question there. Okay. If you want, I can tell you how we're using this in meerkats, but I can also tell you this is people who did stuff, people I talked to, and these are people who funded us. And actually, there's one other thing I wanted to say. So the VC theory result that I gave you, this upper bound, is useless. We all know these bounds are typically not very useful. However, there's a very interesting practical question there, which is, let's say you're Siemens, okay? You're a company that generates these, X-ray machines, right? And what you know is maybe some person, maybe a patient, wants to get more X-rays as they progress through the disease, but there's a radiation budget. So now you can ask, if you give me a bunch of shapes, if you give me a bunch of, tumors or a bunch of breast tumors or something like that, and if you give me a radiation budget, you can say these are the directions, right, that you need to give you the most information, in a way, right? So, that is one of the applications we're trying to go towards, which is a little bit more practical than the VC dimension, and I'll end. Okay. Unless you want to hear about meerkats.
Questions?
So quick question. So
Yeah.
those pairwise distances are everything?
I'm sorry?
Those pairwise distances. If I have, suppose I have the prior over the pairwise distances, what can I do with it?
So, well, one of the things is, for example, I was using a Gaussian process model, right, for the regression, so I can use that, right? I can put a prior over that covariance structure, right? You could.
How far can you go? Can you generate images? Can you generate shapes?
Shapes. So one of the slides that I was showing you, where I wanted to build this random mixture model, that's what I want to do with it. I want to generate random shapes. So I basically want to put distributions, over the sphere, and then use the projective geometry to pull it back to shapes, right? We're trying to do that. We haven't gotten there, right? So that's one of the things I do want to do.
When you compare the two objects, you had this scan over direction V, don't you first need to align them somehow?
Yeah, so this is the point. So everything I showed you was on aligned shapes, right? Now that's one of the reasons why we're trying to extend it to the rotation-free version when you look at the distributions. Aligning shapes is a pain in the ass. So a typical way of aligning shapes is you first do all pairwise alignment, and then you do something like construct a minimal spanning tree, right? Then you go to the minimal spanning tree, compute distances on the minimal spanning tree, and then iterate this until it stops, right? That's one algorithm. There are other ones, right? But this is a really painful thing to do. So that's one of the reasons why we're trying to go to this rotation-free version. We're also trying to write out a scale-free version because I have a colleague who wants to compare neurons of rats with neurons of mice. And they want to, like, I don't know, get rid of size. They want to say that rats are just not bigger mice. I mean, at the neuron level. Yeah.
If we give you a collection of persistence diagrams over a sphere, and it changes continuously over a sphere, can you tell whether it comes from a shape or not? Why along this transform?
I think, I don't know the exact answer to that, but I think what I could tell you, yes, if you give me the continuous things, I could probably tell you if it came from some moduli space. I might be able to test that. I don't know. I'd have to think about it.
I guess it's related to the question of going back, right?
Yeah. I want to say yes, but I also want to be careful. I will think about it and I'll send you an email. But I want to say yes, but it's not always just good to say what you know.
Okay. No other questions? That's like Sayan and all the speakers. And we'll meet tomorrow.